Hi everyone, my name is Xingzuo Zhou.
I'm Yiang.
I'm Shuheng.
I'm Xiyan.
Our research is to predict vaccine uptake rate in the US using machine learning, roughly 1 year after worldwide spread of COVID-19. Two vaccines, Moderna and Pfizer, are approved for emergency use in the United States to protect the public. Given the vaccines have certain expiry date and limited supply, it is vital for government and health officials to have detailed understanding and accurate predictions of vaccination rates in order to optimize both local and global distributions, and implement further epidemiological interventions on vaccine hesitancy. This could be done using machine learning on both clinical data such as daily infections and non-clinical data such as web queries and blog comments. In the past, predictions used either clinical and non-clinical data have been proven powerful. For instance, a computerized reminder system has been made in Salage et al. 1992 to promote vaccination rates. Traditionally, predictions based on statistical methods have been widely applied in the field of public health, and specifically infodemiology. INSEMIC also used the infodemiological data of vitamin research queries to research how the term increased statistically significantly since the pandemic, controlling for seasonal changes. Casey and his colleagues used the multivariate regression to explore the predictive power of not only non-clinical personal attitude towards scientific information, but also the clinical experience of severe respiratory diseases on influenza vaccination rates. Recently, infodemiological studies also implemented machine learning algorithms on non-clinical data to better predict vaccination. Such importance is quantified in Carey et al., where the authors used the supervised random forest machine learning algorithm on area-level indicators of institutional and socioeconomic backgrounds to predict the vaccine hesitancy rate in Italian local authorities and help public health practitioners to run targeted awareness campaigns. In addition to use those common algorithms, Gosset et al. Proposed to use the supervised machine learning of host-winter model in the predictions that captures the seasonal variations across the year to improve accuracy. A part of improve the algorithm for greater predictions accuracy, Hayden et al. Discovered a substantial improvement in prediction accuracy when used both clinical and non-clinical web data, that is, in sample data. In this paper, we combined clinical and web data to analyze variation uptake rates through an infodemiological method. Our group predicted the COVID-19 vaccination rate more accurately, used both clinical data of new daily infections and non-clinical web data of relative web search volume.
Based on the most frequently used words code, we qualitatively chose 18 words from each attitude of positive, negative, and neutral for vaccination from 66 vaccination-related words. These words were then searched for the relative search volume on Google Trends from 21st December 2020 to 20th May 2021 in the United States. The relative interest was treated as web data, while the official daily news cases published by CDC were treated as clinical data. For the outcome variable, the vaccination to expectation ratios were used as daily zero using formula shown. Both quantita and GLM-net packages were used in R for cleaning the dataset qualitative selection of Google Trends search keywords. For statistical and machine learning analysis, we used the Stata module, RMLStata, to run Python packages, Pandas, NumPy, and scikit-learn. We used the three types of models in our analysis. The naive method refers to Hansen's naive baseline, which estimates the expected vaccination by past observations directly. It assumes a constant vaccination to expectation ratio. Besides, simple linear regression was used with positive, neutral, and negative variables representing the calculated interest. We used ordinary least squares to find their coefficient. The model assumes linear specification. We also considered autoregressive model to improve accuracy. 7 legs were chosen by corogram given 7 autoregressive terms. Machine learning approaches were used for higher accuracy as well. They'll also avoid overfitting of the irrelevant features by selecting a reduced set of the known covariate. We apply the support vector machine classification on our regression, which is similar to the linear regression but sets a tolerance level of error instead. And both the rest two are ensemble methods. The boosting classification introduces a strong classifier from a set of weak ones by building an initial model to the training data and then building models to minimize the variance. It has a set of weak classifiers, which is small models. The random forest classification is a combination of bagging algorithm and feature randomness. It reduces the variance of individual classification trees by randomly selecting from the subset of data. Averaging these uncorrelated predictors reduces overfitting problem.
I'll be discussing about the results we have got. In table 3, we use the root mean squared error, which is standard deviation of the residues, to compare and detect large deviations of the prediction from actual y values, and the lowest value highlighted in blue indicates the random forest algorithm has the lowest root mean squared error, and the AR7 plus Lasso has the highest root mean square error of 0.27732, which is significantly higher than all other algorithms. Therefore, we would not include Lasso in our further analysis. In addition, we presented in table 4 a result comparison between each day of actual CDC data of vaccine administered and our predictions made by different algorithms. Our best algorithm, random forest, gives the rather close prediction, but not always in all dates. Therefore, more observations added in training datasets might improve further on the consistency. In this slide, we presented key scalars of the machine learning algorithms we used when applied using tenfold cross-validation on the in-sample data. The accuracy are measured using the explained variance, taking 1 as the maximum value. The training accuracy are rather high in all classifiers, though SVM is slightly lower than the other two. The testing accuracy are high in both boost and random forest classifiers, and this is a way we can truly understand how our model will perform on unseen data for future vaccination uptake predictions. Particularly, random forest has the highest testing accuracy of 0.7274 and the lowest standard error of 0.103. It only uses 8 features compared to 15 estimated in the boost algorithm. In this slide, we presented decision-making of each classifier on optimal hyperparameters lambda to minimize the testing prediction error, i.e. the out-of-sample prediction accuracy in tenfold cross-validation. The optimal index for SVR, boost, and the random forest classification is 96, 114, and 77 respectively. We can observe that learners behave differently, with boosting and random forest showing the best mean test accuracy, but random forest in particular has tighter confidence interval. The worst performing learner is the SVM, both in terms of mean accuracy and the standard deviation. In this slide, the 3 figures on top contains graphical representations of the in-sample predictions in the estimate model. They are the predictions only for the training dataset, and we could see that all 3 models behave reasonably well. 3 figures below are the out-of-sample predictions for only the testing dataset. We could see a strange inconsistent trend in SVM out-of-sample predictions compared to actual observations. However, this trend are consistent for both boost and random forest algorithm.
So let's discuss our results now. First thing we want to do is to compare the accuracy of our predictions. You can compare the accuracy through 2 methods. First one is RMIC, which compares accuracy across all models. And second one is scores, which compares accuracy across all machine learning methods. The principles of the 2 methods are explained by our friend Yiang before. And the definition of predictions is given by the vaccination to expectation ratio, which is the daily first dose vaccination over the number of people expected to be vaccinated in hundreds. It is also defined as probability that unvaccinated individuals receiving the first dose of COVID vaccine. The shortcoming of our predictions is the underestimation of predictions due to the nature of convergence. It also appeared in many other researches. So there are some concerns about our researches. First one is the reverse causality. Luckily, our model addressed this issue. So the protection of COVID vaccines takes at least 2 to 4 weeks, which means the vaccination does not affect new case rates in 7 days. So our exogenous assumption between our variables are satisfied. Furthermore, the new case rates are all related due to the spread of virus, so our relevance assumptions also hold. In this way, we use instrumental variable regression with 7-day data to eliminate potential reverse causality issue. In addition, one limitation of our study is to use Google API solely. For research queries alone, there are many other available services such as Microsoft Bing, and past studies have also reviewed the potential for predictions via other API from discussion forums and video websites. Hence, combining other infodemiological data sources in the future may improve the accuracy further. So in conclusion, the classified random forest gives highest accuracy of 72.74% within sample data. And using the random forest algorithm, those unvaccinated people are anticipated to receive their first dose COVID-19 vaccine with a probability of 0.35% on May 20. And in the future, we are going to use hot winters. This is because the virus is less contagious in summer. And in the past, Gotha predicted COVID-19 infections successfully. And to establish this model, we just simply add further data, and with machine learning, the model will improve by itself. That's all. Thank you for listening.